name's Adam Savitzky. I'm here with Forio Online Simulations to present to you a really exciting new open source language and a brand new IDE for working with it. So the language is called Julia. Many of you stopped by our booth and we've given you the spiel. But the purpose here today is to dive in a little bit deeper and look at the language, look at some examples of how to use it, how to work with Julia Studio. So I'm the product manager for Julia Studio at Forio. I'm also a web developer. My background is in chemical engineering, so I have an undergraduate degree in chemistry. So I've worked a lot with MATLAB, doing process simulation, process control. So I know a lot about just sort of MATLAB. I've also done some work with Python, not so much R, but I have a little bit of a technical background, but now I'm really doing web development. So Julia, as we've told a lot of you, is an open source, high performance technical computing language. So if you've ever worked with MATLAB, if you've ever worked with R or scientific Python, you're going to feel right at home working with Julia. It's designed for similar applications, where you're basically doing general purpose mathematical programming. It integrates basically all the best libraries for doing things like linear algebra, linear programming, statistics, signal processing, string manipulation. That's all there. Because it's an open source language, support for new libraries is arriving all the time. People write stuff, they contribute it, and the language is growing very quickly, both in terms of popularity and support for different packages. So the main differentiating factor about Julia is its speed. So without doing anything special, without having to work at a low level like you would with C or C++ or even Fortran, you get performance that's going to be very close to what you'd expect out of C++. In fact, on many benchmarks, it approaches or even matches the performance of C++. And then about Forio. Forio is a simulation company. We have a platform for developing and sharing online simulations. So we've been working now with Julia for a while. It was announced in February that it was going to be released to the public. We're fortunate enough to have two of the Julia developers here with us today. They got their start at MIT working in the applied mathematics and high-performance computing departments. And they're really the impetus behind all of this. Without them and the other Julia developers, and of course the open source community, Julia wouldn't exist. So we have them to thank for their hard work and their continuing dedication to the community. I'd also like to thank Wes Henny. Sorry, I'm still not very good at saying your last name. But Wes works at Forio. He's the primary developer for Julia Studio. And of course, Michael Bean, he's the founder of Forio and sort of the visionary behind the entire project. So moving on, why Julia? Basically, in the language of the language developers, they were greedy. They've tried everything else, they didn't like it, they wanted something that worked better. And like any hacker, if you don't have it, you make it yourself. And they shared it with everybody. So here's an example of some benchmarks. I cut out some of the other languages because it was too much for the slide. But I'm showing you Julia, Python, MATLAB, and R. And these are some benchmarks. All of the code for the benchmarks is available online. And they just illustrate various different types of algorithms. So Fibonacci is recursive. Quicksort is a sorting algorithm. PySum, iteration. Just to give you an overview of the language. Down at the bottom is matrix manipulation. So basically, all of the languages are relative to C++. So if you see 1.97, that means Julia ran the code in about half the time that C++ would do it. So the next step up would be Python, and then MATLAB and R. And of course, these aren't all inclusive. Some things are going to run faster in MATLAB, for example. And you can see on matrix manipulation, they're all pretty close. But the reason for that is they're all using the same library for doing matrix manipulation, which is LAPACK. It's open source, so I mean everybody's using the same library there. It also has a really nice syntax. So you can work on a very high level with matrices and vectors and things like that for data manipulation. But you're going to get performance that approaches C++. And then also just one nice little touch is you don't have to put asterisks if you're multiplying a constant-defined variable. So that's nice if you're doing a lot of math. You know, it's nice to have. And there's a bunch of other nice little features of the language too, which hopefully we'll get into. And then finally, actually there's one more after this, but one of the more exciting areas of developing the language, and it's actually an active area of research, is parallel computing. How can we leverage distributed systems to do computation faster and more efficiently? And Julia really abstracts away a lot of the difficulty of doing that. So while it's not really, at first I was telling people, well, it's easy to do parallel computing with Julia. It's not, because you have to think intelligently about how you structure your parallel processing. But like message passing, for example, you don't have to manage the internals of that. Julia does it for you. So I expect that's going to get a lot better in the months and years to come in terms of development. And then finally, it's open source. So if you don't like it, you can complain about it, and you can contribute code and fix it. There will probably be a lively dialogue with the language creators. They're opinionated, as they should be, but without the work of people like you, the language wouldn't be where it is. So we encourage you to give back and contribute. So Julia Studio is a product that we're introducing today. It's the very first IDE for working with the Julia language. You can run Julia by downloading it and building from source too. It takes about 2 hours and it doesn't always work. So I think the easiest way to get started with Julia is to actually download Julia Studio. It runs on both Mac and Windows. You can get it at forio.com/Julia. So let's take a look at what some code would look like in Julia. We're going to do some basic linear regression here. So looking at a data set, this is data about some samples of gasoline. And gasoline is a complex fluid, but it's made up of, let's say, there's 3 different components, or 3 different categories of components. And we've measured the composition for a lot of different samples. This is just 4 of them. But this is the percentage breakdown and the octane rating for the gasoline. So what we want to do is try and construct a linear equation that predicts the octane rating of a gasoline based on different component makeups. So we basically have 3 different constant coefficients. X represents the makeup of coefficient I, and epsilon is an error term, basically an intercept if you want to think of it as a line. You can generalize it as an expression of vectors, which would look like this. So X is the input, Y is the output, and beta, which is cut off over here, is our error vector. So this is basically how you'd express it in Julia. Julia has good support for CSV files, so you can read in data from a CSV file. And then what we do on the next line is I construct an input matrix consisting of the columns of data, and I get the output, which is the octane rating, and I just run linear regression. And what it's going to do is it's going to give me give me a vector of output where you have your error coefficient and you have the coefficients to each of the equations. So it's pretty dead simple. And just to give you an idea of the speed that the language is developing at, before I wrote this example, like linear regression didn't support multivariate regression. So I contributed code, and a day later we had support for it in the language. So that's just to give you an idea. If you write code that's useful for you, you can share it with other people, and that's how the language will grow, in my opinion. So let's do a cool demo, okay? Let's save the Apollo 13 astronauts. And the code for this is all available on forio.com/Julia too, so you can download it and play around with it. And we've got basic tutorials from Hello World all the way up through examples of discrete event simulation, linear algebra, you name it, we try and cover it, and there'll be more to come. But, so what happened with Apollo 13, if you recall, is they were going to land on the moon, and they slowed down around 30 hours into the mission. And the idea behind slowing down is they'd be able to fall into the gravity of the moon and land on the surface. But about 60 hours into the mission, an oxygen tank exploded. And that meant that they'd have to abort their mission of landing on the moon. They weren't able to do it. But if they were to continue at this trajectory, they would essentially crash into the surface of the moon because they were moving too slowly. So what they had to do was speed up. And what we're going to try and do is we're going to try and calculate the amount of acceleration that they're going to have to do on the spacecraft in order to not only not crash into the moon, but to slingshot around the moon and then return safely back to Earth. So let's get out of full screen mode here. So let's start by looking at the physics. It's a three-body simulation. We're assuming the Earth is going to be centered at the origin. We have a spaceship, and we have a moon that we're going to assume is moving in circular fashion around the Earth. So essentially, we're just going to use gravitation. And there's going to be two gravitation vectors acting on the spaceship, one that points towards the moon, one that points towards the Earth. And the total force on that spacecraft is the sum of those two vectors. So that's going to look like this. The total force is the sum of the force from the Earth plus the sum of the force from the moon, which looks like this, where m is the mass of a given object and g is the vector. And we know that force is mass times acceleration, so we can derive an acceleration vector at any given point in time based on the distance, the vector pointing to the moon and to the Earth. So it looks like this. That's the vector that points towards the moon. And if you'll recall, acceleration is really just the second derivative with respect to position. So we essentially have two simultaneous differential equations that we need to solve. So the approach that we'll take here is we're going to use numerical integration to simulate the position over time. So let's look at how we actually implement this in Julia. The first thing that we're going to do is define some constants. So I'm going to go over to Julia Studio. And when you create a project in Julia Studio, which you can do by going to New Project, the first thing you're going to get is a file called main.jl, and that's sort of the starting point for execution of any code. So you can see what I'm doing here is loading in some files. So you can see this constants.jl file. I'm loading that in, the value of all these different constants. They're just physical constants, the mass of the Earth, the radius of the body, things like that. So we define those constants, and then we're going to define some types. And types in Julia are kind of unique. You can think of them, if you're familiar with Java, as like a template, or maybe that's a C object, or structs. They're kind of just like objects in a way. They're not exactly, but if you're familiar with object-oriented programming, you can think of it as an object. So I'm going to define a body type, which is going to be a general type for the simulation. A body is something that has mass, position, it can exert and receive gravity. So I'm going to define a type for a body. I'm going to say that a body has a mass, it has a velocity, a radius, and a position. And then I'm saying that the body can take any different type. It can be a type that takes floating point numbers, it can take integers. And this is actually called a parametric type because it's agnostic as to what types you pass it in. But that's not really so important right now. There's plenty of information and documentation about that. But basically I'm saying that mass is going to be a floating point or an integer or whatever type it gets passed in.
What you're doing that is totally optional though. All the type stuff, you can just, if you don't want to do it, you can just take it all out and it still works.
Yeah, absolutely. Typing is optional. You can add it, you can use it if you want to increase performance basically.
So all of them has to be the same T, or you can change the types for some fields?
They don't have to be. They could be specifically float 64, or you could just leave them off entirely, and then it just can be anything.
Yeah.
You get a little bit better performance if you specify the type in this case.
But you could leave off, you could just be body, no T there, and just mass, velocity, radius, position. You don't need to assert any types whatsoever. Doing that to increase performance. But like for example, it's helpful I think to say that velocity is going to be a vector, right? So that's why I'm doing that. Position's a vector, 2 dimensions. So I'm going to create this body type. And then I can create the Earth object, which is a body which takes type of floating point numbers. And I'm going to pass in the mass, I'm going to pass in the initial position of the Earth, or rather the initial velocity of the Earth, the radius of the Earth, and the origin. And see, here's an example of doing without actually explicitly passing in the type. You don't need to do that. So then let's define some more types. I'm going to define a type for a moon by using the type alias command, which basically just creates a new type with all the same stuff that body had on it and calling it moon. And then I'm going to do the same. I'm going to create a new type called command module, which is also an alias for a body. And then I'm going to create a type system, which just has pointers to all of the other stuff. So everything in the system is represented by a system type. So it's going to get a reference to the time of the universe. It's going to have a reference to the Earth. It's going to have a reference to the moon. It's going to have a reference to the command module. And that's what we're going to use as the main object for our simulation. So I'll load that in. I'm going to define that all in a separate file called types, and I'm going to load that in. And then I'm going to initialize some more bodies using so I can now call a command module, create a new command module with some initial information. I'm going to create a world, which is a system, and define all those. And then this is what a function looks like in Julia. So this would go in my main file, right in main.jl. I'm going to initialize the current time. I'm going to set it to 1. And then while current time is less than the total duration of my simulation, I'm going to update my world. And then I'm going to increment the current time. So then I need to write this update function, right? On every iteration, I need to update the world. So update takes a couple arguments. It takes me, which is itself. So you can see here I'm saying update, and I'm passing in world, which is a reference to the world that I created after the system itself. It also takes the time. So I'm going to pass in the time of the system. And then I'm going to update the time of the system by setting me.time equal to time. And then I'm going to update the moon. I'm going to update the command module. And then I'm going to just return the system. Now, Julia uses something called multiple dispatch, which allows you to define a function that works differently based on what type you have. And that makes sense for mathematical programming languages. You can take, for example, the inverse function, INV, okay? So let's go back to Julia Studio. I'll show you how that works. But the inverse function. You can see here that it takes all of these, so inverse of an integer, inverse of a complex, inverse number, inverse abstract array. You might want to invert a matrix, right? You also might want to invert a number. If I invert 10, I'd expect to get 1 over 10, 0.1. But if I invert, so let me move this up. It's kind of hard to see. I guess I don't know why I can see that. But let's say I create a matrix just of random numbers, a 10 by 10 matrix. There it is. If I call INV on A, it's going to invert the matrix instead. So that's an example of using multiple dispatch. And that's a really powerful paradigm once you start using it, because you're able to express the same function for different types. So that's what we're doing. That's what we're doing here. We're defining this update method several times. But see, for this, in this case, it takes a system. The update method for the moon will take a moon, and the update and the command module update method will take a command module. So that's another reason to use types too. But in any event, here's a good example of that. I'm not going to go through it now, but it's sort of an example using different types of people. Well, actually, we could go through it now. I have a type for a person, and the person has a name, and I define a function called person, which calls that person by their name. So I might construct a new person for my mom, and I'll call mom. But then I might want to define a call person function for my boss or for the doctor. And I want it to have different behavior if I'm calling the doctor. I'm not going to call my doctor mom. So what I'm doing here is I have my original definition for call person. And I have another one that specifies this is going to be the call person function gets called when I'm calling my mom. It says, hey, I love you, mom. And then similarly, I have one for my doctor. Sorry I'm late, my boss's name. And likewise for the doctor. So we're going to define update methods specific to the command module and specific to the moon. So here's what's happening when I call update on the moon. first thing I'm going to do is I'm going to update, let's see how we're doing time first. We're doing okay. So the first thing I'm going to do is I'm going to update the moon's position by calling this moon position function. Moon position takes time. So what it does is it calculates the moon's position by using the initial angle and the period of the moon to figure out where it's going to be at any given point in time. Okay, and then the update for command module first calculates the acceleration, which uses that equation I showed you. It's just basically relating to the forces on the body at any given time, depending on where the moon and the Earth are. So it's going to return the acceleration, and then I'm just going to use Euler's method to numerically integrate this function. So I'm going to update the position to be the velocity, and then I'm going to increment the velocity for the next iteration by the acceleration. Pretty simple, right? Velocity is going to increase by acceleration. Position is going to increase by velocity. So then just another little function I wrote. So now that would work great, right? Except you end up getting a lot of error if you use Euler's method. So we're going to use a modified version called, I think it's pronounced Hund's method. I don't know how to say it, but it's spelled like this, H-E-U-N. But basically it uses an adaptive step size. And the first thing we do is we calculate the Euler's velocity and position. And then we look ahead to the next step. And then we average the two values. And we use that value instead of the Euler's value. So basically, we define all of these update methods. And then we create a vector to hold our positions in time. And then we pop it into a big loop. So in main.jl, I'll show you what we have here. I have this simulate function, and I define a variable called boost. That's going to be that's going to be the decision we change. So what happens if I speed up 15 meters per second at the command module at the specified time. And then I'm going to define an initial step size, and I'm going to define a couple burns that happen at various points in time. And then while current time is less than the total duration, I update the world, the current time, and I pass in my new adaptive step size. So then I calculate the new step size, and then I push my values into a vector to represent my XY coordinates at any given time. And then I output it to a CSV file, which allows me to do some plotting. But if you end up running this, you're going to see something like this if you plot the XY values. So I start here at the Earth, I take off. This is if I do nothing, by the way. Really what would happen is I would crash into the moon, but we don't have a moon here to crash into. So we go around the moon, and then we actually end up missing Earth. We wouldn't make it back. And then here's, it's kind of small, hard to see, but for various, actually I can probably open this in a new tab. If you set boost equal to 10, it turns out to be pretty much right. We're going to come back and land, actually that might not be right. Probably go a little faster though. We should speed up a little bit more. But like, here's an example. If I use a boost of, if I actually slow down by 100 meters per second, this is what would happen. I go flying way off into space, no good. And then if I speed up way too much, we have a similar problem. So I don't even know what happens there. That looks terrible. That's a pretty comprehensive example. If you can get through that in Julia, chances are you should be able to find your way doing anything. Kind of an interesting example using a real-world case. So let's go back to my presentation now. But where is it? Oh, I think it was. Small screen, it's hard to figure out what's going on. Okay, so we've saved the Apollo 13 astronauts. Where are we going with Julia Studio? The next step is to add graphics. So you see I did all those plots in Excel, and nobody wants to do that. So we'd like to make Julia not only the best, I mean, we want it to be the best language for technical computing, but we'd also like it to be the best language for graphics and plotting. Like, let's have that be a feature of the language. We really believe in data visualization in general, and I think there's a lot of potential there. So there's a lot of active work that's been done in the open source community, and we're going to be looking at integrated graphics in the next couple weeks. There's going to be a Linux version coming. That's in the works. Debugging, that's a harder problem to solve, but we'd like to give you the capability to actually debug your code. Right now, what you have to do is sort of print out output various parts of your program. Code completion. We'd like to be able to include some code completion, especially if you're new to the language and you're not as familiar with sort of what methods are available. I think that would be a nice feature to have. And we're open to suggestions as well. And if you have questions about the roadmap for the Julia language, Stefan and Jeff are the people to ask, because they're the gurus in that department. So you can download the slides here at this link if you want to see them. Again, the link for downloading Julia Studio is forio.com/Julia. We have postcards up here with a link, so you won't forget. And does anybody have any questions? Yes?
So I think you started off by mentioning that Julia lends itself well to cloud computing.
Absolutely.
So can you say more about that? How does it, how is it better?
Yeah, so it works on the, and I'll definitely defer to Jeff and Stefan at some point, but the way it works really is on top of this idea called remote references. So I can specify, what's the syntax for creating a remote reference?
Well, you don't usually do that explicitly.
Okay.
I go there and put some
You can do this at spawn, right?
Yeah.
So essentially what you do is you can request,
That's
you can add a processor, then you can use this spawn thing and just say what processor you can either do it with, you can specifically say spawn at and pick a processor, or say spawn and it'll just pick a free processor. And you can just put an expression there and it'll send everything it needs to actually evaluate that expression on the remote side for you. And what you get back immediately is a reference to that computation, which you can then pass around and use in various ways, and at some point say, okay, I want to wait for this to be done because I'm ready for it now. So what you're doing is you're saying, getting this other machine to go do some work for you while you go do some other stuff, but then when you're ready for it, you will block on waiting for that. And you can pass those around to different machines, so it's pretty easy to put together a complex computation.
Remote asynchronous execution.
Across multiple physical machines.
Across multiple physical
multiple
machines.
cores, multiple machines. Yeah. Any of those.
And it's easy to set up a connection between machines that are on the same network, or do you do SSH tunneling?
There's a ton of people that use SSH to start processors.
So we're going to add SSH tunneling, because that'll be
That's like
very
a
shortly soon, so then you can even be in like different data centers if you want to.
And then we have, we've built up higher level of abstractions on top of that. So there's a parallel loop that's built on top of this. There are distributed arrays that's built on top of that. So if you're doing something that's very data parallel, you could just use a distributed array, and then you don't even really have to think about parallelism that much.
Yeah. Then you just say things like, add these two distributed arrays together, and it just does everything that it needs to do. That algorithm itself is written with the slower level stuff. So it's sort of like a layering of building blocks that you can use at different levels of abstraction.
I should show you the output of this code, by the way. The way to run stuff in Julia Studio is just F5. There's also a run button over here. And it just loads the main file and it executes everything. You can see it runs pretty quick in 0.17 seconds, which is, I think, pretty darn fast, given how much actual number crunching it's doing. The total duration of this simulation, let's look for it. It's so 12 times 24 times, so 12 days on a second-by-second interval. And we're adapting the step size to be bigger or greater than 1 second, depending on what error is calculated to be. So it's doing a lot of iterations. Remember, it's operating on vectors, and to get this kind of performance in a problem like this, in the past have to use C++ for Fortran. And if you are a C++ programmer and you like doing that, that's great. But I'd encourage you to check out Julia and play around with it a little bit. And I think you'll find that it's much higher level, but you're not really sacrificing all that much performance. So.
Yeah, question. So for loops in MATLAB are ridiculously slow, and so what happens here?
They're ridiculously fast.
Yeah, within a factor of 2 of C. Simple.
For loops are almost as fast as C.
Yeah, it can be even better.
There's like function call overhead is a little higher than C. So it kind of depends on what you do, but mostly it's very close.
Somebody wanted me to demo what it would be like to convert a 1,000 by 1,000 array, because apparently it's fast in MATLAB. We wanted to see if it was fast in Julia. I think that's an example though of them using the same library. But I'll show you here. I'll show you a couple examples. You can invert a 1,000 by 1,000 matrix. Let's look at how long that took. Okay.
You want to do a lapse?
What's that? 0.12. Oh. Similarly, you take the eigenvalues a little bit slower. It's a big